Welcome to Understanding Levers Part 2. Let's start with a YouTube clip on the lever.
If you're sitting on a teeter-totter, looking for someone to teeter-totter with, and then a big fat guy comes along, what do? Do you want to risk it? Now, there's an easy way you could have avoided that. Two easy ways, in fact. You could have either have asked the fat guy to move nearer and nearer to the middle of the teeter-totter until you balanced. Or else, you could have made a little adjustment to the teeter-totter before he sat down on it. And then, you would also have balance. Both methods really boil down to the same thing. You see that support the teeter-totter is resting on? Well, scientists have a fancy word for that. They call it a fulcrum, which is simply Latin for a support or pivot. Anyway, whether the fat guy moves himself closer to the fulcrum, or whether you move him closer to the fulcrum by moving the teeter-totter, the result is the same. The distance between him and the fulcrum becomes less than the distance between you and the fulcrum. And that's the secret of successful teeter-tottering with people heavier than yourself. Or for that matter, the secret of the successful balancing of any object with any other heavier object. If you want to balance a 100 Newton weight with another 100 Newton weight, you place them both at an equal distance from the fulcrum, let's say 2 meters. But if you want to balance a 100 Newton weight with one that's twice as heavy, you move the 200 Newton weight nearer and nearer the fulcrum until it's in just the right place for the two weights to balance. Now you know how to lift a 200 Newton weight with a force of only 100 Newtons. It looks as if you're getting something for nothing, doesn't it? But you're not. Don't forget that the 200 Newton weight is nearer to the fulcrum than you are. How much nearer is it, in fact? 1 meter? So the distance between you and the fulcrum is exactly double the distance between the 200 Newton weight and the fulcrum. That means that you have to move your end of the teeter-totter exactly twice as far as the weight moves. You exert a force of 100 newtons through 1 meter in order to lift a weight of 200 newtons through half a meter. What do you win on the...
Let's talk about this now. Let me go to my slideshow. So, let's review because this is part 2 of levers. The anatomy of a lever, we have a fulcrum, which is the point that the lever rotates. We have what's called the input force, that's the force we exert on. And we have the output force, that's usually the resistance or the load that we're lifting. So here's what it looks like. Output force, that's where we put the load. Fulcrum, input force. And again, as a review, the 3 types of levers, class 1, class 2, and class 3, depend on the arrangement of these 3 things. For example, in this picture, we have a class 1 lever. The other thing I want to review is some calculations. We can calculate something called the mechanical advantage of a lever by 2 ways. One way is if we measure, like in this picture, the length of our force or effort arm, and so in this picture, if we push down here, this would be our effort arm, it would be 1 meter. So we can put the number 1 there. And let's say we're lifting this box. That's now the load, or sometimes called R, the resistance. L for load, same thing. And it is 0.5 meters. So 1 meter divided by 0.5 meters would give us the mechanical advantage. 1 divided by 0.5 is, of course, 2. There are no units for mechanical advantage. And what does that really mean? Well, that means whatever our effort is on this side, we would double what we did on the other side. So if our input was 4 newtons and we pushed down with 4 newtons, we could lift a load that was 8 newtons for weight. And so on. Let's say we had a 16 Newton weight. That would mean if it had a mechanical advantage, we'd only have to put in 8 newtons of force. Again, the mechanical advantage has to do with how much we multiply our force. So in essence, the MA, or another way to look at the mechanical advantage, is the output force, which is the load, output, divided by whatever your input force is. Let's do some calculations. Let's calculate the mechanical advantage of this lever. So we have two ways. If we knew what our output force is, which we do, 200 newtons, and we knew what our input force is, we could find the MA. However, in this picture, we don't know what our effort or input force is. Okay, so let's try the second formula. If we knew what the length of our effort or force arm was, and we knew what the length of the load or resistance arm was, we could find the mechanical advantage by dividing the two. So let's see our picture. Here's the fulcrum, and here's our effort. And lo and behold, it gives us a distance of 6 meters. There, then, is our length of effort arm. 6 meters would go here. And here's the box, which we call our load or resistance. And we go from the fulcrum to the end. And there, or this, is 2 meters. And that would be the length of the load arm. So 6 divided by 2 gives us an MA of 3. Okay, so if the box was 200 newtons and the MA was 3, what would that mean? Well, remember, output force divided by input force equals the MA. So 3 goes here. Our output force is 200. So all we have to do is find the input force. This is a divided by sign. So over here, 3 is the MA, 200 goes here, divided by question mark. So 200 divided by what equals 3? 200 divided by what equals 3? Well, this number's got to be smaller than 200 for it to equal 3. Let's get out our trusty calculator and see if we can find this out. $200 divided by 3 equals 22.2. Let's see if that works then. 22.2. So let me turn my pen back on. 3 equals 200 divided by 22.2. That should work. So notice again, the MA is bigger than 1. In fact, it's 3, which means I only have to put in 22.2 newtons of force to lift a box that is 200 newtons. So what have I done? I've multiplied my force by 3 over on this side. Let's try one more. Here's another lever. This time it's a class 2 lever, like a wheelbarrow. And we need to find the mechanical advantage. Well, one way is to take the length of the force arm and divide it by the length of the load arm. Or, of course, another way is if we knew the output force in newtons, and we could divide it by the input force, divided by input. Okay, I have an output force. Here's my resistance. There's my box. That's the output, 150. But I don't know what my effort is, my input. So I can't use this formula. Let's try the bottom one. Force arm. Well, here's my force, and it goes all the way to the fulcrum, and that's 9 meters. So I know that. Let me plug that in there. 9 meters divided by the load arm. Here's the box, and it goes to the fulcrum, and the picture's saying that's 3 meters. So 3 meters. Lo and behold, 9 divided by 3 gives us an MA of 3. Okay, now all we need is this. How much is the effort? Well, let's use this formula. Mechanical advantage, which is 3 equals output force, that's the box, 150, divided by input force, that's my effort. I don't know that. Well, let's figure it out. 150 divided by what equals 3? I think it's 50. I can check. 150 divided by 50, does that equal 3? Yep. So, how much effort would I need? Only 50 newtons. Only 50 newtons here to give me an effort of lifting a box that's 150. So there's 2 more examples of how to calculate levers.